Conservation of matter. Conservation of mass. There is no new matter. So this is an important concept. Matter is neither created nor destroyed in a chemical reaction. Matter is neither created nor destroyed in a chemical reaction. Now, a chemical reaction is different than a nuclear reaction. A nuclear reaction, significant changes to the matter can happen. You can create and destroy matter using nuclear changes. But that's like, you're playing with Legos, that's chemical changes. Nuclear changes with Legos would be you go out to the garage and you get out the acetylene torch and you're melting the blocks, or you get the hacksaw and you're cutting the blocks in half. Okay, it's extreme. Nothing that we do in this classroom will change the mass. Okay, there's conservation of mass. That means that the mass stays the same. So in a chemical reaction, it says the changes in mass are so minute that they can be ignored. Yeah, there's really no change in mass. And when we have a physical or a chemical change, the total amount of matter remains constant. Now, with a physical change, this is usually pretty easy to understand. You take an ice cube and you melt it. Does the mass of the ice cube change? No, that's a physical change. Now, when you burn something, it may appear that the mass changes, right? You take a log, bring in this big old log, and you stick it in the fireplace, which we can't do anymore because we never have any burn days. But anyway, you put the log in the fireplace and you burn it. And what's left when it's all done burning? Some ashes. Do the ashes weigh the same as the log that you brought in? No. What happened to the mass of that log? It went up the chimney. Most of the wood gets converted to carbon dioxide and water as gases that go off into the air. And so what you're left with is some remnants. If you did this in a closed system where you collected all the water and carbon dioxide that were produced, you would find that the mass does stay constant. It's just that it's not in that solid form anymore, and so it's hard to weigh. So an example with that butane lighter. If we burn 58 grams of butane in a lighter, it's going to react with 208 grams of oxygen, and it will result in 176 grams of carbon dioxide and 90 grams of water. Now, those are not numbers that you can just pull out of the air, but we can do an experiment and they can determine this. And if we look at the mass of the butane and the oxygen, those were the reactants, the two things that we're combining, total mass is 266 grams. And if we collect the carbon dioxide and the water that are given off from that reaction and find the mass of that, it's the same. So even when we burn something, when we do a chemical change, the mass, the total mass, doesn't change. If it appears to change, it's because there's something getting away that you're not aware of. Now, these problems give students fits. Suppose 12 grams of natural gas combines with 48 grams of oxygen in a flame. The chemical change produces 33 grams of carbon dioxide. How many grams of water form? It's actually a very simple problem masquerading as a very hard problem. It's just 12 plus 48 minus 33. Okay, so you've got, can't write with a highlighter, you've got gas and oxygen, right? So 12 grams of that and 48 grams of that. And those are reacting and forming carbon dioxide and water. And it says 33 grams of carbon dioxide, and there's water, and it says how many grams of water. Conservation of mass. The mass of the reactants, which is what, 60, has to equal the mass of the products. So it must be 27. It's just adding and subtracting. There'll probably be a question like this in the exam, and about half of you will lose your minds and think I'm persecuting you with this horrible problem. Any questions? The mass you start out with is the mass you end up with. Conservation of mass.